Cool. So I've been taking a look at the next three, and they should be fairly easy. I think A3 should be really easy, actually. We can quickly, because if I read well, I can apply the operation twice. So the idea here would be if I if I apply a Hadamard twice, but like I apply a Z gate in here, so I'm gonna get the qubit to be on. Whereas if I apply the X gate twice with the Z in between as well, I'm just gonna get the qubit to be off. So that should be easy to distinguish. We can give it a try. So the signature we get here is this one. So I'm gonna head to the program keys to kind of test this first. And this is going to be, so I'm going to just do this, okay, and test solve. Okay, so the unitary is here, so I'm going to just copy over this whole thing, and my code goes here, and so it's using one qubit, right? So that should be it. And what we're doing is we're doing so we're applying, let's say, the X gate, and we're applying the Z gate. So we're doing this to the qubit. We're applying the Z gate to the qubit and then the X gate to the qubit, right? And so then we measure the qubit, and then we reset the qubit. So we reset the qubit. Oh, got it done. So we reset the qubit, and if we measure, so it's an X, right? So what do we want? 0 if it was a Hadamard. 0 if it was a Hadamard. So, and if it was a Hadamard, okay. So basically, what I should do is that if it's 1, it means we have Hadamard, so we return a 0. Otherwise, we return a 1. And if the result is 1, so in this case, the result will be 0. And so we return a 1, right? But basically, the actual, sorry. So, here I can actually try and solve it like properly, and say this is unitary and this is unitary, and so we're going to give it a, for example, we're going to test solve for X, and that should actually work, right? So, and I kind of almost, I'd say I can copy the whole thing, submit, and then call this just solve, and that should really do the job. I'm quite convinced that does it, so I'm going to go ahead and submit it. Submit solve, submit, and then see what happens. Yeah, so it outputs 1, which means it goes to the else. And if we put a Hadamard and we run it, then I should get a 0. That should allow me to distinguish. Okay. Running on test 1. Accepted. Nice. Okay, cool. Go back to the problems. So we've done these. This one is a bit more complicated, I think, A4. So let's go and take a look at this one. So here we need to distinguish between the identity gate, the CNOT 1, 2, CNOT 2, 1, and the swap gate. So the trick here is going to be that, not export, clear all. So we want to distinguish between this operation, then between this operation, then between the swap operation, and between kind of doing nothing, right? So exactly, and let me put the amplitudes in here. How many times can we use the gates though? Because I'm afraid in just one run it will be difficult, because the problem is going to be to distinguish between doing nothing and doing a swap. If I have like this combination, which allows me to distinguish between these two. It doesn't allow me to distinguish between between the doing nothing versus this one. So, but if I take a look, if I take twice, I can apply the gate twice, and this is what we need to do. So this is the signature. So we're gonna use these as signature. Copy the body of this one. Get rid of these. So we've got the unitary in here, and we can apply it 2 times. And so here we've got now qubits, like an array of 2 qubits. Okay. Okay. So what is it going? What should I do? How should I do it? Because if I can apply twice, it means I could measure and say, I could measure both qubits. And if it's 1, 1, I know that it's this gate. If it's, so I probably need a, what I probably need is to measure qubit 0. So gates go here, and then let res 0 be this, let res 1 this, and that already resets my qubits. And then I guess if res 0 and 1 equals 0, so I guess we'll kind of have to do some logic in here, but I guess is it else if is correct, or is it like elif or something? Elif, yeah. So I guess we can just go with all the different possibilities. So else, so this is 0, 0, 0, 1, 1, 0, right? And then the else is the 1, 1. So kind of we have the 4 possible cases. I guess we're applying the unitary in here, so we're just doing like unitary on qubits, and I might wanna set the qubits to something first, right? So I'll be okay. So if I measure 1, 1, so what if I do this? Maybe it's an easier one. Okay. Okay, so that allows me to distinguish 2 cases up front, but then I can't distinguish between these in the first pass. Okay, so if I do this already and I get like, 0, 1, 0, right? Like 1, so the first qubit is 1 and the second 0. So this is the this case. Then then it's a C0 1 2. And what do we need to return? Okay, C0 1 2 is 1. So here we return a 1. C0 1 2. In the case we measure 0 for the first and 1, so this is, we're going to return, I guess that's a 2, and that's a C0 2 1. Right? 0 0 is not the case. Okay, so 0 0 is not in there, so I'm just gonna so far work on these cases. So if it's the first qubit is 0 and the second is 1, it's a C0 2 1, C0 1 2, and now else I probably should do something else, right? So the qubits are now reset. Okay, in this case I'm using I'm setting the 2 qubits to 1. So what I do is I probably do x do this. Well, x needs a qubit, so qubit 0 and x qubits 1. So I'm preparing the stating here that I need. and I'm running the unitary and I'm measuring this. Else, and now I'm gonna probably do something else in here, which is, okay, now how can I distinguish these? Well, it's easy, right? So if now we set this one to 0, like, yeah, exactly. So now we would basically set only both reset. So we're gonna set the second qubit to 1. So I'm just gonna do this, and then we will run the unitary again, the qubits, and we'll measure. We'll measure again, and I guess it's as simple as saying that long if, but so in this case, if the and probably only I just need to measure one qubit, right? Like if the first qubit is on, then it's a swap. Okay, so if the just need to measure this, and if this is 1, this will turn into an else. So if it's a 1, it's a swap, and if not, it's an identity. It's identity, exactly. Which means the swap, for the swap we need a 3, and for the identity we need a 0. And that should do it. Can we test it? Solve. We can't easily test it because this is no. Okay, but I need to. What's going on here? Why? Qubit 1, qubit 0. Expecting. Oh. And here, call expression. An expression used as a statement must be a call expression. Okay. No. Why? What is the problem? Already exists. Yeah. Whatever. Result 2. Can reuse those for some reason. I don't know. What I should do is just in case, after doing this, I should do reset. Here it's 0 and reset. Here it's 1. Just in case. What is going on here? Yeah, just in case. Oh, how can I test this? So how can I test this? Need a function that takes 2 qubits and then applies one of those. So I need, like, that's what I was trying to do before operation. Secret unitary. And this takes basically it takes basically the same type of argument, right? It's an int. If I test that. Not all paths return. Yeah, okay. And so we're going to test secret unitary. secret unitary, and we'll, no, that doesn't have any parameters. We're now going to just call, no, again, losing my time. What I want to do is I want to have I can't directly test solve, because if I put in the actual unitary, it doesn't have this signature, so I should have like a operation, for example, test swap, right? That has this signature, so I can give it to test solve. Test swap, test solve. A figure call does not match the expected type qubit. And so in here I give it like a an array of qubits. So I'll say qubits, 2 qubits, qubit. Why is it not? Is this, why is it complaining about this? The type of given arguments does not match the expected type. Got an argument of type int, expecting one of this returns the unitary in that way. So it returns, yeah, if I'm using that as a parameter, it should return a unitary, it should return a function that does this. It should return a swap. It should return these, like it should return, so whatever. That's basic programming. How would I test that? I'm trying to think about, like, how would I? Yeah, I guess I'll just do this by hand. It's gonna be easier. So test solve. I guess I'll just take these and say, what if the unitary is a swap of qubits 0, qubits 1, so now terminal, I'm gonna run this. So for a swap, I should be given a 3. But my intuition is that this works, so I had to pop it here. All this thing just 3, just solve. Let's see if that works. I'll test in the meantime. So submit in queue. So it works for the swap. It works for the C0. So the C0, C0 1, 2. So I should be getting a 1. Yeah, accepted. Okay, it works. Cool, 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 cool. Good. I think I'm gonna leave this one here. So I did 2 in this video, and now we've got problems. Okay, so we've got this one, which is a bit trickier, right? It's about distinguishing between these and these, and I was chatting with a couple people about it, and because I didn't really understand really what the R1 equivalence is, or what is the, because Q sharp RZ gate and Q sharp R1 gate. I think the difference. So I want to try to understand what's the difference, right? Because in Quirk we have an RZ gate that we can use, and we have a Z gate, but like R1 seems to be. We can probably play with custom gates if we've got the formula here. These, as far as I know, is a global phase. So it seems R1 is adding a global phase, and RZ is not adding a global phase. RZ is Z, okay. So RZ is Z. But it's kind of funny, right? Because, oh yeah, RZ is... No, because the Z in Quirk actually adds a global phase. So I don't know, that's confusing. Why can't people just use a standard notation for that? It's going to make it tricky. But my intuition tells me that I should... okay, so what is the... Precision measurements to figure out which unit was to return 0. So RZ, you are allowed to apply the given operation exactly once. You can pass it to any rotation angle that you choose. You have an operation which takes a single qubit operation unitary. Two parameters similar to RZ and one intrinsic gates. The first parameter is the rotation, and the second is the qubit. I think we're going to have to use some kind of phase kickback effect to kind of play with these. Let me just like, I think that if you do something like that and you take a look at this qubit, you will see like that, and you will see there's no phase kickback. Why is that? I thought there should be. And if we apply an RZ gate in here, so here there's a phase kickback. Why? I thought that's the one that's not adding a global phase. Like if I say pi, that's adding a phase of 90. That's kicking a phase of 90 degrees. So that's kind of the difference, right? If I do something similar with the Z gate here, oh, okay. So wait a second. So this qubit is fully on. Ah, that's why it is. It has kicked the phase. Okay, that's it. Here it is. So it's kicked the phase of 180 degrees. Yeah. And so it turns on fully on, but this one doesn't. So there's a difference, but this is again like non-deterministic, and if we can only use this operation once, that's not going to help us, because here we kind of have a 50-50 chances of getting the answer right. So I have to figure out another way or an extra set of gates to apply to make those two different. But I'll think about these later. I'm gonna Gotta go now. Gotta go now.